All right, so we are back at it. We have Unit 8. And we're looking at some more things with sequences and series. First thing that we need to look at in Section 1 is how to approximate the errors. So I talked about when we created power series, Taylor series, McLaurin, anything like that, it's just an approximation. So what we're trying to find is the possible errors that are created sorry about that, phone. And there's a couple different ways that we would do it. So in the first part, we're looking at alternating series. So remember, the alternating series is anything that we have the -1 to the n power, and we're fluctuating between a negative and a positive value. So we can calculate the error by finding another term. So let's say we went to the third term. To calculate the error that a third term would give us is we just go to the fourth one. We just go to the n plus 1 term. Okay, so we go to the next one. And that's going to give us the error. So let's go ahead and take a look. It's a little easier to see once we get rolling into some examples here. So approximate the sum of this series by using the first 6 terms. So what we're going to do is we're going to list out the first 6 terms. So we're going to plug in 1, and we're going to find out what that would be. So the first term would be 1. Plug in 2, we would have a negative value. So we have 1 over 2 factorial, or just 2. Plug in 3, we have a positive value. And we're going to get 3 factorial, which is 6. Plug in 4, 1 factorial. You can write them out as factorials. You can write them out as the actual values. Does not matter. So 1 more. Okay. So given the first 6 terms, we're approximating the sum. So what we're going to do is we're going to put this in the calculator, and you can actually type a series out. If you go into math, and it's down by the integrals, I can tell you exactly what option it probably would be here. Let's see. If we go to math, and it's probably 0 in most calculators, so it's summation, and it has the little sigma symbol. So if we go there, you can actually type that in, or just type all these values out, and we would get something like 0.63 194. So that's the value of those 6 terms. All right. So easy enough. That's something we've done. In example 2, it says find the upper bound for the remainder for the approximation in example 1. So we went to the first 6 terms. So what we're going to do is we're going to go to the next term. So if we were to go to the 7th term, we're going to plug 7 in, and we would end up with a positive 1 over 7 factorial. Okay, and we can calculate that in the calculator, and that would be 0.000198. Okay, so our remainder is actually less than or equal to the absolute value of this number. Just so happens it's positive, so we don't have to have absolute values, but that's what we're going to look at. So this is the, we'll just put R. So that's remainder. Okay. You might want to write out remainder, just so you don't confuse it with your R value for your geometric series. Alright, so that's the upper bound. And then in example 3, find upper and lower bounds for the actual sum. So what we're going to do is we're going to take our calculated value from example 1, and we're going to add on this remainder error. Okay. So we know that it is actually, and there's really no lower bound on this one because we know we're adding this. If we went to this next term, we're going to add. And if we kept going, we're subtracting and adding smaller values. So it's actually going to max out here. So what we can go ahead and we can write our this out. And if you wanted to make it look really nice, we could say our series is going to be equal to, and we can list out all of our terms. But we don't have to. So we can say this. So this will be between our 0.63194 from example 1. Okay. And less than our 0.63194 plus our error. So our value is going to be somewhere between here. So our calculated value and our calculated value with our error added on. Okay? Which ends up being 0.6321429. Okay, so that's how we would show that. Example 4, approximate this series with an error of less than 0.001. Okay, so what we're going to do, we're going to write out, just like we did example 1. We're going to list out our first few terms. If we plug in 0, we end up with 1. And plug in 2, we're going to end up with a 1/2. Plug in, plug in 0, plug in 1, plug in 2. Plug in 3, and plug in 4. Okay, so we could keep going on down the line, but what we want is we want an error of less than 0.001. So as soon as we get to a term that has a value less than this, we can stop. So if we look at 1/8 factorial, that is actually 0.00024. Okay, so that right here, and let me box that in here. This value, that term, gives us 0.00024, which is less than 0.001. So what we can go ahead and is we can ignore this value, and we can just look at this part of the series. So that's what we're going to want to calculate. Okay, and it actually turns out to be 0.54028. Okay, so that's our approximated value for the series that would be have an error less than 0.001. All right. Last one for this video, and then I'll make another one. So use the elementary series to find the actual value of the series in example 4. So if we look back at example 4, we need to find what this series is equivalent to. Okay, So the series from n equals 0 to infinity of this would be, so we should recognize this as cosine. So we're just missing the x to the power. So what we have to do is we have to figure out what our center is. So our center in here, and if you need help finding what the center would be, just get with me and we can talk through that. But the center here, the thing we're evaluating is 1. So this is equivalent to cosine of 1, which actually turns out to be 0.54. 030. So it's pretty close to our series approximation. Alright, so like I said, that's it for this video. I will make another one. We're going to talk about another type of error approximation. And if you have any questions, just let me know.